I guess. Okay, hello everyone. Today, Dr. Frank Camerel from France joining us to Grad Talk. I guess it's the 28th online presentation. We will be talking about gels, design and application, but before we jump into presentation, I would like to make a brief introduction about our host. Frank Camerel, a chemist, studied in the University of Nantes, and he has also his PhD from the same institute, I guess, no? At Institut Mathieu Jean Roxel, excuse my French pronunciation.
Is this correct?
After that, he moved to Max Planck Institute of Colloids and Interfaces with Professor Antoinette and Dr. Carl Fall as a postdoctoral associate, and he worked on ionic self-assembly processes with charged organometallic molecules and inorganic cluster ions. And he is working as CNRS researcher and joined the Professor Ziesel's group, where his research activities turn on the design and the synthesis of luminescent liquid crystal for application in optoelectronic and the study of gelation properties of amphiphilic fluorophores functionalized by hydrogen bonding fragments. Okay, without further ado, we would like to listen your presentation, Dr. Frank Camerel. Okay, here we are with you. Thank you.
Okay, thank you very nice for your introduction. I will, yes, speak today about gels, design, characterization, and I will try to give some application, of course. It will be a basic introduction on gels, mainly on how you can design gels on small molecules. So I will try to show this today, but first I will show you where I am exactly. So this is the map of France, and we are in the area of Brittany here on the west part of France. So in this area, you have another area which is called Ille-et-Vilaine, and in the main town in Ille-et-Vilaine is Rennes, where I am. So this is the town of Rennes, and we are on the east part of Rennes in the campus called Beaulieu. So you have many buildings in this campus, and we are here in the building 10. This is a picture of the building 10, and this building is called Institut des Sciences Chimiques de Rennes. So this is a building catering almost all the chemistry in Rennes. So this institute belongs to several legal entities. So the University of Rennes 1, the CNRS, the INSCR, and the INSA. So we are currently to almost 300 permanent researcher, so with a professor, assistant professor, and technical staff. And we have almost also 280 PhD students and postdoc. So we are quite a big institute.
Yeah.
So today, as I told you, I will speak about gels. So let's see some basic introduction. So we can define a gels as a material consisting of interconnected chains swelled by a solvent. So you have a picture here showing chains which are interconnected, and these chains are swelled by a solvent. So this is a picture obtained by TEM with lecithin, which form gels, and you can see how can look the solid structure inside the gels. So if the cross-linking is made by strong covalent bonds, you speak about chemical gels, and you have the example of vulcanization for some polymers, or you can speak about physical gels, and here you have more weak interaction between the chains. Okay. So how you can define a gel? So you can say that's a mass of homogeneous colloidal nature, translucent, and of soft consistency. So you know how looks a gel. And you can define a gel as a three-dimensional network of solids diluted in a fluid. Here it's a solvent. Okay, so you have two pictures of gels, and the most simple definition to see if you have a gel is just to take your suspension and to turn your vial upside down and to see if the solution flow. If it's not the case, you can say that you have a gels. But the more physical, I won't say, the proof for gels is come from rheological studies. So you basically measure under, how would you say, auxiliary condition, the real part, which is the storage modulus, sorry, and the imaginary part, which is the loss modulus. So the storage modulus corresponds to the elasticity and the loss modulus to the viscosity. And you have a gel if you have an elastic modulus stronger than the, much larger than the viscosity modulus. One order of magnitude, it's enough to define this as a gels. Of course, if the elasticity is null, you have only a viscous Newtonian solid. And if the elasticity is a value and the viscosity is null, you have an elastic solid. So as I said, you have two types of gels. So you have the chemical gel. So you have a cross-linking which is due to covalence bond. So this compared to the gel's irreversibility. As soon as the gel is formed, you have no reversibility. But this allows to obtain robust gels. On contrary, physical gels, you have weak bonds due to weak interaction. This allows you to have reversibility, and you can develop some stimulable gels. So these gels can be stimulated with the temperature, by mechanical constraints, also by some other stimulus such as salt effect or pH. So what we call gelators, or more precisely gelling agents, are substances which allow to give the food or material the consistency of a gels. So you probably know that you can extract some gelling agent from animals, especially from bones, which is called gelatin. You can also extract from some gelating agents from plants, so pectin from algae also. And you can also synthesize some gelling agents such as polymer or small molecules. So concerning the application, you can find gels in many fields, and especially, for example, in cosmetics. You all know the gels for the shower, the gel for the hair, the gels for the nails, and that's all. And you can find gels in in many cosmetic materials. You can also find gels in medicinal application or pharmacy. I don't know what to say. Like gels or gels for echography, but for example, for toothpaste or for implants. You can also find gels in industrial materials, I want to say. So like you can find gels in shoes. It can be used as electrolyte in battery to avoid the flow of the electrolyte if you have some problem with your battery. You can find this in paints, but also in pencil, for example, for the color. And of course, you know, another big application of gels, which is in the food industry. You can have some candy. You probably know these small bears. You can also have this jelly cake, and you use gelatin or agar-agar as gelling agent for making some cakes. And you can also find some in sauce. So one well-known gelling agent, for example, is agar-agar. Agar-agar is a polymer composed of two polysaccharides, agarose and agaropectin. So you have this fragment and these fragments, which are mixed in various ratio. And when you take this powder, you put some liquid, you heat the solution to dissolve the polymer. And as soon as you cool down the solution, you have interaction between the polymer. You have expulsion of water, creation of hydrogen bondings, and you have aggregation of the polymer and interconnection of the polymer. And this leads to the network which immobilize the solvent and make the gels. So this is how it works agar-agar in your kitchen. You can also obtain gels. So as we have seen here, polymer. So you have several polymer, I say. You have also, sorry, I come back a little bit. You have also some alginate, agar-agar, which are also some natural polymer. Gelatin is also a natural polymer. But you can also develop some gelling agents from small molecules. And we call this gelling agent low molecular weight gelator, as to compare with polymeric gelators. So this small molecule will first interact each other between them to make fibers through weak interaction. And after this fiber will collapse to make molecular strands will collapse to make fibers. And after, the interconnection of these fibers in the solvent, which will lead to the formation of the gel. So as you can see, probably you already see this, that the formation of a gel is a subtle balance between solubility and crystallization. If the molecule are soluble, you will not have gels. And if the molecule want to aggregate and crystallize as a large object, they will precipitate, so you will not get a gel. So this is really a balance between solubility and crystallization. So how to design, I want to say, small molecular weight gelators. So basically, you can say that you have two-part molecules. The first part will be the structurating part, I want to say, and the other part will be the solubilizing part. So we speak about two-player system. So the first player is responsible for unidirectional cohesion of the molecule, and the second part is responsible for the solubility and prevent crystallization. So you have an example here of a molecule in which you have a hydrogen bonding motif, and this hydrogen bonding motif will allow the molecule to pack into a one-dimensional structure. So usually we use amide, urea, some peptide. You can also use sugar or alcohols to drive this one-dimensional stacking. And after, you have these long alkyne chains which allow the solubility of these molecular strengths. You can also introduce some additional stacking interaction, such as p-stacking, van der Waals interaction, and also some additional hydrophobic, hydrophilic interaction. So let's speak more precisely about some example I have developed. So for example, here you have a molecule. As you can see, we find this two players system. So the long carbon chain for the solubility, the amide function for the directionality of the aggregation. And here we introduce some additional PP stacking. and especially but also by doing this, we introduce some fluorescence property, because here it's a pyrene, which is known for luminescent property. So this molecule is able to gel, for example, here you see DMF. And DMF, you have in DMF, when you take this molecule, you heat and you cool, and you have these gels. And if you look at this gel under UV light, you can see that this gel is strongly luminescent. And now, if you look at the morphology of the gel by scanning electron microscopy, you can see that you have formation of fiber due to the aggregation of this molecule inside the solvents. We have also shown that the size of these fibers, or especially the diameter of these fibers, is really sensitive to the nature of the solvent, and the size strongly depends on the solvent. So after we took these fibers, and as they are luminescent, we had a look to these fibers by confocal microscopy, and we also confirmed by confocal microscopy that we have luminescent fibers. And after we put these fibers in field effect transistors, and we have shown that these kind of fibers can allow to conduct yes, electron and holes with almost the same facility. So you can, for example, expect to use these fibers for electronics, for example, as nanowires. I also developed another gelating agent from this, what I call platform. You will see why. So here also you have these two-player parts. So the long carbon chain for the solubility, the polar and rigid part with the amide function. So here you have, in addition, a graphene sites on which we can add some molecules, and here you have, of course, the hydrogen bond donor acceptors for the one-dimensional stacking. So we don't speak too much. So here we can graph, for example, ligands, which are, for example, ici bipyridine or terpyridine, phenanthroline, sorry, phenanthroline here, and terpyridine here. So this is interesting because by introducing these ligands, you can add some metals, you can make some complex with metals, and this allows you to obtain metallogelators. And metallogelators are also interesting because you can add new properties inside the gel, such as electrical, magnetic, or luminescence properties. But you can also introduce new geometries. So I will show you what we obtain with this platform with the phenanthroline function. So here, this is the crystal structure we obtained. So you can see that you have a one-dimensional stacking of the platform in the center. And we remove this, we remove the phenyl with the long chain for clarity. But you can see that you really have one-dimensional stacking stabilized through hydrogen bonding. So we made also a complex of these ligands with the copper one, and we got these copper 1 2 ligands complexes. And we also got the structure. And here, on contrary to the other stacking, we don't have a one-dimensional stacking because the hydrogen bonding is engaged into an intramolecular interaction. So this prevents the one-dimensional stacking and the stabilization of the one-dimensional stacking through hydrogen bondings. So, and this has a strong consequences, yes, because you can form gels with the free ligands, but as soon as you put the metal, you cannot form the gels because you have less free available hydrogen bonding motif. So this is a picture we obtained through scanning electron microscopy of the gel. And here also you can see that we have fibers with the gel, and you can form gels And you can confirm that you have hydrogen bonding with IR, for example, using IR spectroscopy. So you can see that here that the availability of the hydrogen bonds is really crucial to obtain these shapes. So next example is one with the terpyridine. Here you have the terpyridine fragments. So this is the structure of the terpyridine molecules. And here also we get this one-dimensional stacking stabilized through hydrogen bondings. But if you look more in detail the crystal structure, you can see that you have this one-dimensional stacking stabilized through hydrogen bonding. But you also have a stabilization of layers through the pp stacking between pi stacking between the terpyridine fragments. So in this structure, you cannot say that you have only one-dimensional stacking, but you have two-dimensional stacking. And you can see after a model which has been constructed by adding the long carbon chains. And what we, in fact, observe here is that you can obtain gels with this compound, with this terpyridine compound. But in this case, it's not a gel made of a three-dimensional network of chains, but it's a gel made by the swelling of layers, more classically as soap and things like this. So here it's a lamellar structure which gives these gels, and it's not the classical way of small molecular weight gelators. Another example, so this time we take these terpyridine complexes, molecules, and we make the complexes with iron. So you can see that now the gels is really colored. You don't have anymore now layers, but this molecule is able to form gels, for example, here in cyclohexane. And this is a structure we made from this compound make gels, but also is a liquid crystalline material. So this is a model for the of the organization in the liquid crystalline phase. But here we managed to obtain a gels with a metal which is highly colored in this case. So you can put ligands, you can make metallo-gels, but you can also put directly, for example, fluorescence molecules like this body P derivative. And here, in this case, you have a trisamide platform, which is even stronger. And here, this is the gel you can obtain under normal light. And as soon as you use UV light, you can see that you have a really strong luminescence. So these gels, so we check the morphology of these gels, but this time we don't have really fibers, but we have what we call fibrils, which are small fibers, really small fibers, but the interaction of these fibrils lead to the formation of these gels. So you can see here that many type of aggregate can lead to the formation of gels. It depends how they interact with each other. So here it's a normal transmission electron microscopy image, and here it's an image which has been obtained by cryofracture. So this is another technique to directly obtain the morphology of the gel with the solvent. Donc here we managed to obtain a strongly luminescent gelling agent by introducing this body B derivative. What is also interesting, you can use this body P derivatives as a probe to check how the gel is formed. So this is the normal absorption spectra and emission spectra of this body P here in dichloromethane. You can see that you have an absorption below 520 nanometers, and you have an emission around 530 nanometers with a good consumer yield around 50%. So as I said, this is the normal emission spectra of the molecules in a good solvent. Let's say here dichloromethane, you have only one emission bond, which is characteristic of body P. But if you put now this molecule in a bad solvent, you have two emissions, one coming from the isolated molecules, and another one coming from the aggregated molecule, which are called excited dimers. And you have a new emission at higher wavelengths, so around 580 nanometers. So you see here, as soon as the molecule aggregates, you have a new emission which is coming. And you can use this to probe how the gel evolves with the temperature. At high temperature, you don't have the gels, so you have the solution. And in the solution, you have only a single emission coming from isolated body P. As soon as you cool down the solution, the gel starts to form, and you have first formation of excimer here at 580 nanometers. And when the gel really form, you have longer aggregates, and you have a new emission here, which appears as a shoulder, which is due to extended aggregates. So you can really follow the process of the formation of the gel by starting from isolated molecules to dimers and to multimers. So this allows to also to determine in some ways the sol-gel transition. So the process is completely reversible. If you heat the solution, you first lose these shoulders. You have only this excimer emission, and after you have only the monomer at high temperature. So here it's another platform with this time we put an alkynyl function with a silyl or without silyl, so protected or deprotected. And we check the gelation, and here this is what we got. So with the it's always with the silyl protection, but with C12 chain we have this, and with C8 chain we have a solution. This you can say that it looks like a gels, but in fact it's not a gels. It looks like a gels when you turn the vial upside down. The solution does not flow, but it's not a gel. If you look closer, you can see that inside you have really stiff fibers, rigid fibers. And this is not a gel, this is a three-dimensional crystallization, which look like the formation of a gel, but it's not gel. As soon as you touch this suspension, it's break and you start to flow. So it's really, really fragile. So this is not a gel. You have no elasticity in this case. So take care to this. It's not because it does not flow, but it's the gels. This is the message. Okay, another example with this platform. So after we make this silyl and you deposit, you can also make some complexes. Here, for example, with platinum terpyridine fragments. So we use two types of chain, linear chain or branch chains, and we check first the aggregation of this molecule in solution. And as you can see here also, the color of the solution is really sensitive to the aggregation of these molecules. In good solvent, you are yellow, and in bad solvent, you are almost dark green. So this is due to the formation of aggregates and to the appearance of new bonds which come from platinum-platinum interaction. So we make gels. When you use higher concentration, for example, in dodecane, you are able to form gels which are made of fibers. So this is a transmission electron microscopy image. And these aggregations here also is stabilized by hydrogen bondings through this amide function, but also by the stacking stabilized by platinum-platinum interaction. So here, this is a model which has been constructed by molecular dynamics. And you can see that, in fact, you have a stabilization of fibers, which are stabilized by hydrogen bondings, but also by platinum-platinum and platinum-alcene interaction, which are revealed also by the color of the gels. Another example, you can, as you can see, you can put whatever you want. Here it's another complexes with lanthanides. Here we use neuropium complexes, and as you can see, you can make gels which are strongly luminescent in the red due to the use of europium. But if you put terbium, you will have green gels, and you can change the color. And we check also the emission, and you can see that the emission is almost the same, but it's a little bit different due to the supramolecular interaction. So as you have seen, you can use hydrogen bondings to form the gels. You can also use metal-metal interaction, but you can also use electrostatic interaction. This is another example. Here, the gelling agent was constructed by using electrostatic interaction between the solubilizing part and between the rigid part containing hydrogen bondings. So this allows to build in some way one-dimensional fibers, and you can easily change at the periphery the solubilizing part, through electrostatic interaction. So, for example, if you take this lipid with this platform, you can make a ionic association, which lead to the formation of gels, for example, here in DMF. So you can really use several types of weak interaction to build this gelling agent. Another example, which has been developed in collaboration with David Bardelang at that time it was in US. So this is a dipeptide you can synthesize, which is protected by a smoke here, I think, if I remember. So this molecule is able to make gels in various solvents. So, for example, hexadecan, cyclohexane, and water methanol mixture. Alors, if you take the complex directly as a powder, you heat the solution and you cool, but you don't have a formation of gels. You have a precipitation. The way to obtain gels here is to use sonication. And if you sonicate this compound in solution for a period of 1 to 4 minutes, you have gel formation. So we check by SEM what was happening during the time. And at the beginning, you have sheet-like particles, which are not soluble in the solvent. As soon as you apply ultrasonic stimulus, you have the reshaping of these sheets into fibers, which leads to the formation of the gel. And if you continue to use ultrasonic stimulus, you have another precipitate which appear as stiff ribbons, which are beta sheets. So this is the recrystallization, reshaping of the powder, which lead to the formation of the gels. And this has been demonstrated by DSC, NMR, and infrared diffraction also. So this compound was also interesting because you cannot make gels in water, but you can make gels in alkane, I want to say, or petroleum. And you can use, for example, these kind of molecules to gels, for example, petrol or kerosene here, in this case, for example, in water. So you can selectively make a gels of the kerosene inside on water. So this can be used, for example, as for decontamination of oil splits. This is an example of what we can do with this kind of molecules. Another interesting work for me. Here, usually you see that you need a flat molecule to be able to stack them as a one-dimensional compound, but you can also try to design some much more funny things. For example, we use this cubane. which look like a cube. So you have 4 copper atom and 4 iodide atom, which are in the summit of this cube. And you also have on each copper a ligand, which can be a phosphine derivative. So you can have several types of what we call cubane copper iodide cluster. And depending on the ligand you use, you will have several properties. And in particular, this compound interesting because they can show thermochromism. So thermochromic properties. So thermochromism is when you change the temperature, you change the color. You can also have some rigidochromism with this cubane. So when you change the pressure, you can change also the color. And you can also have some mechanochromism. So as soon as you apply mechanical constraints on these materials, you change the color. So this type of compound are really interesting because they are sensitive to several types of stimulus. So we were interested to see if we can develop some gels from these cubane type molecules. So we have developed, for this, we have developed new phosphine ligands. So this time we introduce also carbonates, but here we have this amide hydrogen bonding motif, but we also use, here it's cholesterol, which are known to be good for to develop gelators. So we developed these 2 molecule phosphine derivative, which change mainly here the size of the chain between the 2 fragments. So these 2 phosphine derivative can easily be synthesized. And after we make the cubane, okay, we obtain the cubane in good yields. So after we check the gelation abilities of this cubane in several solvents. So when you synthesize the new molecules and you want to know if it's a good gelator or if it is a gelator, you have to test several solvents. So for this, you introduce your powder into a solvent, you heat the solution and you cool, and you see if you make a gels or not. So we do this for all the compounds in for these 2 compounds in various solvents, and we check if it was insoluble, soluble, or if it makes gels. You have several possibilities, and it can be soluble, it can be soluble, it can precipitate after heating, or it can make gels. In fact, you have 4 possibilities. And we found that the cubane with the shorter ligands was able to form gels in cyclohexane. And this was the only example. But we were lucky, we have 1 gel. So after we checked the morphology of the gel, and in this time, we found that the gels are formed by some what we call beaded light filaments. So this is like small spherical particles which aggregate together to form these one-dimensional chains. So it's not the same aggregation process which takes place here. It's again another aggregation process. So we had here some TEM, ACM, TEM, and confocal microscopy image showing these networks. And this network seems to be due to the formation of nanospherical particles at the early stage of the gel formation. And we wanted to see if it was true. So we can use here also the property of this cubane to check this. So first we check if these gels were thermochromic gels. So we have this cubane, and in fact, when you are at room temperature, you have a green emission. And when you go to low temperature, you have a blue emission. So this comes from the particularity of this cubane, but you can see that you have a gel here which can change its color with the temperature. But you can also use the rigidochromic properties here, for example, to probe the dynamic of the gel formation. So when you start at high temperature, you are in solution, and as soon as the gel will form, you will the environment around the cubane will be more and more rigid, and the luminescence will increase. So what we see here at high temperature, we have a low luminescence, and as soon as we start to cool, we have an increase of the luminescence. And at a certain stage, you have a really strong increase of the luminescence, and after, you have a plateau. And this is due to the dynamic of the formation of the gel. At the beginning, you have this formation of these nanoparticles. And as soon as the amount of nanoparticles is sufficient, you have a critical concentration, and the gels start to form, and you have a really strong increase of the luminescence. And when the gel is finished, you reach a plateau. So you have three-step stage, or you have three steps: the nanoparticle growth, the gelation part, and the gel part. So you can use the properties of this cubane to follow the dynamic of the gelation. Currently, I'm working on, so this was quite old work, but now I'm working on another class of metal complexes, which are called metal bis dithiolane complexes. So I'm particularly interested in these complexes because they are quite easy to make, because you have this metal which is coordinated by 4 sulfur, and you have 2 dithiolane ligands. So these complexes are interesting because you can use several types of metals, and depending on the metal, you have various properties. These complexes are thermally and photochemically stable. They show good absorption property in the visible, but also, as you will see, in the near IR region. And this is why I'm particularly interested in these complexes. They show redox properties, and depending on the metal you use, you can have some radical spaces, so you can have some magnetism. In addition, as you can see here, these complexes are have a square planar geometry, and they can easily be functionalized on the dithiolane parts, so you can develop discotic and discotic molecules for liquid crystalline materials or gelatins. So this is one of example we have studied. So here you can make, for example, the gold complexes. And what is interesting with the gold complexes, it can be isolated as a neutral molecule with radicals. So these molecules show some liquid crystalline properties, and this compound form columnar hexagonal phases, some columnar mesophases of hexagonal symmetry from between 80 and 120 degrees Celsius. So you have a columnar mesophase, which contain radical spaces. So you have some magnetic interaction. And in the liquid crystalline phase, you have antiferromagnetic interaction. So the magnetic moment is really low. But as soon as you reach the phase transition between the crystal and the liquid crystalline phase, you change the interaction between the radicals, and you have an increase of the global moments, magnetic moments. And you can see that if you cool and heat around the thermal transition, you have an hysteresis here which appear. And this can be interesting, for example, for data storage or something like this. But I was also interested to see if this molecule was able to make gels. And in fact, this molecule is soluble in hot linear alkane. And when you cool down, you have formation of gels. So here, this is a picture of gel. So it's dark green gels, and inside you have fibers. So due to the stacking of this molecule in two columns. So these gels are formed by a three-dimensional network of interconnected fibers, here with a diameter of 60 nanometers, extended over several micrometers long. So you can also use these magnetic properties to try to find the sol-gel transition. And here is what we have done with the squid apparatus. We measure the moment, the magnetic moment as a function of the temperature. So in normal or pure dodecane, you have a constant increase of the moment with the temperature. But in the gels, you can see that you, at a certain point, you have a break in this curve, and you have a stronger increase of the moment around 50 to 55 degrees Celsius. And this corresponds, as you can see by DSC, to the sol-gel transition. So you can also detect this sol-gel transition by magnetic measurement, which are imported here by the presence of radical molecules. So the gel obtained here were not really strong. So we developed a strategy. So we changed the design of the ligands to obtain more rigid molecules. So you tell me when I have to stop. Huh?
We have time a little bit more.
Okay, I think I will almost stop in 5 minutes, let's say.
Yeah.
So we developed the design of these molecules by introducing this cholesterol function, which are well known to import gelation properties. And we managed here to obtain gels, really strong gels, with low quantity of gelating agents. So let's say the ability of molecules to form gels is measured with the quantity of molecules you need to make the gels. So I want to say stronger gelling agents, strong gelling agent will be obtained when you will put less gelling agents to make the gels. So here we use really low quantity of gelling agents to make strong gels. So this is a really good gelators. And here you can see that you can make gels in various alkane, linear or cyclic alkane, and they are really stable. So here you see that it's always a problem of design and you cannot predict exactly what will happen, because you can see that here with short chain you have gels, but with long chain or without chains you have precipitate or it's insoluble. So it's like for liquid crystalline materials, you cannot predict. You have to do and to test before to say if you will have gels or not. So we managed to have strong gel here. So we check the morphology, and we have also fibers. But if you look here more closer with AFM, atomic force microscopy measurement, you can see that you have fiber, but you have some line on these fibers. And these lines are due to the presence of helical stacking. And you can confirm this helical stacking by doing some CD measurements in the solvents. In good solvents, you have no CD signals, but as soon as you form the gel or you are in a bad solvent, you have a CD signal due to the formation of right-handed helix in this case. And you can also use these CD properties to probe the aggregation and de-aggregation of the gels. So this is a model we made from this picture and the size of the molecule, and you can make a model which gives you a view of how the molecule can be stacked. We also try to put more cholesterol function, because at the beginning it was working. So we say we will put more cholesterol function, we will get more stronger gels, but it's not the case, because this time the molecule cannot perfectly packed. You need much more strong, larger amount of molecules to be able to form a gels, and the gels are not so good. Okay, so this is not always the good things to say, okay, I will put more, I will get more. This is not the case here. So we didn't know exactly what to do with these complexes, but nevertheless, as I said, these molecules strongly absorb in the near IR region, and these complexes are non-luminescent, so they are able to convert NER light into heat, and so what we call photothermal effect. So we use this photothermal effect. You can quantify this photothermal effect under irradiation. You can find that these molecules are able to convert around 20% of the light into heat. So what we have done is here, okay, this gel is, well, they are not so good, but it's gel. So what happens if we put a laser on the gel? And as you can imagine, I don't know if it will work, of course. No, I think the film is not working, but no, it's okay. It's not working. So I will summarize here. As you irradiate the gels, you have this photothermal effect which takes place. So the light is converted into heat. And as soon as you hit the gel, you destroy the gel and the gel starts to flow. So you pass the sol-gel transition and you go to the solution. And if you leave the solution after, you can go back to the gels. But you can, of course, do this by the normal way, by heating and cooling. But you can also use a laser in this case to destroy the gels, thanks to this photothermal effect. So I will not go too much here now. I will stop here, I think. I will just, I hope I was not too long.
No, thank you.
I will just go at the end to thanks all my co-workers. So don't worry, I will not speak about all these things. So I just want to thank all my co-workers which have been involved in this work. As you imagine, many people have been involved. And I thank you, of course, for your attention.
Thank you, Frank, for this engaging and delightful presentation. Now we can have the questions and comments. If we have many colleagues attending from the chemistry department, I can see. So if you have any question, you may raise your hand, or you may, if you don't have the proper microphone, you may use the chat box. I can read the question for you if you have any. For the last one, the video was not working. Is that only the heating and cooling effect, or it's just the steering as well? No, right? It's
No,
just
there is no steering. It's only the irradiation process which lead to. I don't know if I can show you this.
Yeah, that's really cool.
Yes. No. Yeah, it's working now.
Oh, yeah.
You see here the laser arrive here. We see the impact of the laser on the other side. And as soon as the laser irradiates the molecule converts the light into heat. So you heat the gel. So you go from the gel to sol phase.
Okay, photothermal effects.
Photothermal effect. So I'm using this photothermal effect a lot now. It's my main research area now. It's not on gels, but it's more on photothermal effect.
Thank you. Okay, any questions? Huriye Hocam.
Yeah, dear Frank. Yeah. I can ask just one question. In the molecule you showed, amide function seems to be very important for the formation of the gels. So is this the main linker that we use for the formation of gels? But you showed also at the end of your presentation another kind of linker. Which one is the best?
Which kind of linkers? As you see in many cases, not in all the cases, and you can form gels without hydrogen bondings, but you must certainly obtain, and you must certainly obtain stronger gel if you use hydrogen bondings. It will drive the aggregation, and it will also reinforce the molecular interaction. So usually it's better.
Okay, so hydrogen bond is enough, and the linker is not really important. The nature of the linker.
Here, for example, no, I don't know.
Okay.
See, everything
Here
is
it's
important.
different, yeah.
Everything is important, but you have to find the right balance, as I said, between the solubilizing part, the aggregation part. So this is a really, if you put too much hydrogen bonding motif, you will have precipitation.
Okay.
If you put too much solubilizing parts, you will have soluble molecules. So you have to find the right balance to get these gelations. This is not easy, but you have to think about the design.
Okay, so then can we say that it's difficult to predict?
Yes, it's what I say. It's like for liquid crystalline materials. You cannot predict if you will get a liquid crystalline phase from which temperature to which temperature, and if we can stabilize this type of aggregation of. We have some idea, of course, like for the liquid crystalline materials, we have some clues how to design these molecules, but we cannot predict if it will work in fine.
Okay, well, thank you very much for this nice presentation. It was very interesting for our students.
Thank you. We have students from the chemistry department. They may also ask questions, or if they hesitate, they can use the chat box. I can read the question for themselves. Or everything is really clear, and so we don't have to ask any questions, huh, Frank?
Yes, but I try to make something easy. I hope it was
very straightforward and clear. So
I don't know how to do difficult things.
So I guess that's all. Huh? Everything is clear for everyone. So I would like to thank you again, Frank, for accepting our invitation.
But thank you for the invitation. It was a pleasure.
I hope in the near future we would like to host you in our institute as well.
It is planned that I come at one stage in Istanbul, so I hope so soon.
Yeah, we hope to have Frank at the university very soon.
Okay. Again, on my university's behalf and the institute, I would like to thank Frank for accepting our Grad talk presentation. And I hope to meet you all for the next week. We will be talking about power electronics and power systems. That will be on Thursday. Thank you for everyone for attending the Grad Talk seminar for this week. Please like and subscribe our YouTube channel and social media accounts. Thank you for everyone, and have a nice evening. Thank you.
Bye.
Thank you, Frank. Thank you for the organization.